On February 27th, 2026, scientists confirmed something that sounds almost impossible. Earth has just detected radio waves and X-rays that were emitted 12 billion years ago. Not 12 million, not 1 billion, 12 billion years. Before Earth existed, before the sun was born, before our galaxy finished forming. Somehow, something from that ancient universe just reached us. Imagine this. A signal left its source when the universe was still young and just 15% of its current age. It traveled across expanding space for 12 billion years, through colliding galaxies, through cosmic voids, through the stretching fabric of space-time itself, and only now, in our time, did it finally arrive. And when astronomers looked at what sent it, they realized they weren't just seeing a distant object, they were witnessing a monster. The object is called ID 830. At first glance, it looked like a quasar, a bright beacon powered by a supermassive black hole. We've seen quasars before, but this one was different because it wasn't just bright, invisible light. It was blasting out powerful X-rays, and at the same time, powerful radio waves. That combination alone made scientists pause. Then they measured its age, 12 billion years old. That means we are seeing it as it existed when the universe was just 1.8 billion years old. Now here's where things get strange. When researchers calculated its mass, the numbers didn't make sense. ID 830 already weighed 440 million times the mass of our sun. Let that sink in. 440 million suns compressed into a single gravitational well. For comparison, the black hole at the center of our own Milky Way, Sagittarius a star, is about 4 million solar masses. ID 830 was 100 times larger, and it existed billions of years earlier. That's like discovering a fully grown skyscraper in a city that was just founded. It shouldn't have had time to grow that big. And yet, there it was. But the real shock wasn't just its size, it was how fast it was growing. Using ultraviolet and X-ray measurements, scientists calculated how quickly this black hole was feeding, and what they found broke one of the most fundamental limits in astrophysics. ID 830 wasn't just growing fast, and it was growing at about 13 times the Eddington limit. Now, if you're not an astrophysicist, that might not sound dramatic. But in the world of black holes, the Eddington limit is like the cosmic speed limit. It's the maximum rate at which a black hole can consume matter before its own radiation pushes that matter away. Imagine trying to pour sand into a funnel. If you pour too fast, the sand piles up and spills over. Nature is supposed to prevent black holes from overeating. Radiation pressure pushes back, accretion stabilizes, growth slows down. That's the rule. ID 830 didn't follow the rule. It was feeding at 13 times that limit. 13 times. And that wasn't all. The X-ray luminosity revealed extreme activity in the inner accretion disk, the region of superheated plasma swirling just outside the event horizon. Meanwhile, the radio emissions suggested powerful jets, beams of relativistic particles shooting out at near light speed. For decades, astrophysicists believe these two states rarely coexist at extreme levels. Strong X-ray emission usually corresponds to one mode of accretion. Strong radio jets suggest another. Seeing both blazing simultaneously? That wasn't supposed to happen, yet ID 830 was doing exactly that. It was as if this ancient black hole was ignoring the instruction manual of physics. So now scientists are asking a terrifying question. If this existed so early in cosmic history, what else was happening in the young universe that we don't understand? Because here's the deeper implication. Black holes don't start big. They're born from collapsing stars, typically tens of solar masses. To reach hundreds of millions of solar masses takes time, billions of years. But ID 830 didn't have billions of years. It had less than 2. So either it started much larger than we thought possible, it grew at impossible speeds, or our entire model of early black hole formation is incomplete. And that's why this discovery is shaking astrophysics. Because it's not just about one object, it's about rewriting the story of how the first cosmic structures formed. Think about the early universe. It wasn't calm, it wasn't orderly, yet it was chaotic, dense, turbulent, massive primordial gas clouds collapsing, the first stars igniting at some of them hundreds of times more massive than our sun, galaxies forming through violent mergers. Maybe, just maybe, black holes in that era weren't following today's rules. Maybe the early universe allowed shortcuts. Maybe growth was explosive. Maybe limits we consider fundamental were temporarily broken under extreme conditions. An ID 830 might be a fossil from that wild era, a relic of a time when gravity ruled without restraint. But there's one more twist. Researchers believe this extreme feeding phase, this super-Eddington accretion, may have been temporary, possibly triggered by a sudden influx of gas, or something even more dramatic. The black hole may have torn apart and devoured a massive primordial star, not a normal star like our sun. Yet at a hypothetical early universe giant, hundreds of solar masses, if such a star wandered too close, it would have been shredded, compressed, superheated, its matter spiraling inward in a catastrophic feeding frenzy. And for perhaps 300 years, this black hole would have blazed brighter than entire galaxies. 300 years. In cosmic time, that's the blink of an eye. But that blink was powerful enough to send signals that would travel 12 billion years and arrive in our telescopes in 2026. Let that sink in. What we are seeing isn't happening now. It happened before Earth formed, before dinosaurs, before the Milky Way looked anything like it does today. And yet its light is here, right now. This is what makes astronomy so humbling. When we look into deep space, we are not just looking far away. We are looking back in time. NAD 830 is not just distant, it is ancient history, a chapter from the early universe finally reaching our page. And it's telling us something unsettling. The early universe may have been far more extreme than we ever imagined. In the next part, we'll break down exactly why this black hole shouldn't exist, and why its growth rate is forcing scientists to reconsider the so-called cosmic speed limit. Because if ID 830 could grow this fast, then maybe the first generation of black holes grew up much faster than we thought, and that changes everything. In the universe, even monsters have rules. Gravity has rules. Light has rules. Energy has rules. And black holes, as terrifying as they are, also have rules. One of the most important is something called the Eddington limit. If you want to understand why ID 830 is such a problem, you have to understand that limit first. Imagine a black hole feeding. Gas and dust spiral inward, forming a blazing accretion disk. As matter falls closer, friction heats it to millions of degrees. It glows intensely, especially in ultraviolet and X-rays. But here's the catch. Light pushes. Radiation carries momentum. When that radiation blasts outward, it pushes against the very gas trying to fall inward. So there's a balance point. Gravity pulls in, radiation pushes out. At a certain feeding rate, those two forces balance. That's the Eddington limit. It's not a suggestion. It's not a guideline. It's a physical equilibrium set by the laws of electromagnetism and gravity. Go beyond that rate, and radiation pressure should literally blow away the incoming material. It's like trying to run up an escalator that's moving down. Eventually, you can't climb any faster. Well, for decades, astrophysicists have relied on this limit to model how black holes grow. You start with a seed, maybe 10, maybe 100 solar masses. You let it feed steadily at or near the Eddington rate. Over hundreds of millions or billions of years, it grows into a supermassive black hole. Slow, gradual, predictable. That's the textbook. Now enter ID 830. When researchers measured its ultraviolet and X-ray luminosity, they weren't just estimating brightness. They were measuring feeding rate. And the numbers didn't align with theory. ID 830 wasn't growing at the Eddington limit. It wasn't even slightly above it. It was growing at roughly 13 times that limit. 13. That's not a rounding error. That's not observational noise. That's a cosmic red flag. Because if the Eddington limit is a speed limit, ID 830 wasn't going 5 miles over. It was drag racing through a school zone. Now here's why this is terrifying for astrophysics. If black holes can grow 13 times faster than expected, even temporarily, then our timelines for early universe structure formation may be wrong. Remember, this black hole existed when the universe was only about 1.8 billion years old. That's barely enough time, under normal growth rates, to reach a few million solar masses from a stellar seed. But ID 830 was already at 440 million solar masses. So under strict Eddington limited growth, you simply don't get there in time. It doesn't work, unless something allowed it to cheat. So what could allow a black hole to exceed the Eddington limit? There are a few theoretical possibilities. One idea is super-Eddington accretion. In certain extreme environments, matter might flow inward so densely that radiation becomes trapped. Instead of pushing outward effectively, the radiation gets dragged inward with the gas. Imagine trying to shout against a hurricane wind. Your voice doesn't push anything back, it just gets swallowed. If radiation is trapped like that, the black hole could continue feeding at rates far beyond the traditional limit. But here's the problem. We've seen hints of super-Eddington accretion before, usually in smaller systems like stellar mass black holes or certain ultraluminous X-ray sources. But nothing at this scale, nothing this early, nothing this massive. ID 830 is like finding a toddler bench pressing a car. It suggests either early universe gas environments were much denser than we thought. Black hole seeds were born far larger than current models predict. Or the Eddington limit behaves differently under primordial conditions. Any one of those would be a major shift in astrophysics. But the data doesn't stop there. Remember how ID 830 emits both intense X-rays and strong radio waves? That combination is another problem. Typically, black holes show different modes. In one mode, you get strong accretion disks, bright X-rays but weaker radio jets. In another mode, you get powerful jets, strong radio emission, but a different disk structure. Seeing both maxed out simultaneously suggests a transitional or unstable state. It's like a car somehow running both its nitro boost and maximum fuel efficiency mode at the same time. That's not how engines work. Yet this cosmic engine was doing exactly that. So what does that mean? It could mean we caught ID 830 during a rare, violent episode. A temporary feeding frenzy, a cosmic binge. The researchers estimate that this super-Eddington phase may have lasted only around 300 years, 3 centuries. That's nothing in cosmic time. But during those 300 years, the black hole may have gained mass at a staggering rate. And that short burst could be enough to explain its oversized mass so early in history. Still, even temporary super-Eddington growth raises deep questions. Because once you allow black holes to grow this way, you open a door. If one did it, how many others did? Could early galaxies have formed around rapidly growing black holes? Could black holes have shaped galaxy formation more aggressively than we assumed? There's an even more unsettling implication. Now, what if black holes formed first? In standard models, galaxies form and black holes grow within them. But what if in the early universe, massive black holes formed quickly and galaxies assembled around them? That flips the narrative. And ID 830 hints that this possibility can't be ignored. Think about the early universe again. It was denser, hotter, more chaotic. Gas clouds weren't neatly organized. Mergers were frequent. Massive stars, far larger than anything we see today, may have lived short, violent lives. Some theories suggest that the first generation of stars, so-called population 3 stars, could have reached hundreds of solar masses. If one of those collapsed directly into a massive black hole seed, you might start much bigger than our typical stellar remnant models. And if that seed immediately found itself inside a dense gas reservoir, it could begin feeding at extreme rates almost instantly. That's one possible pathway. But it's speculative. What's not speculative is this. ID 830 exists. We detected its X-rays. We detected its radio waves. We measured its luminosity. We calculated its growth rate. The data is real. And it doesn't comfortably fit our expectations. This is the kind of discovery that doesn't immediately rewrite textbooks, but it plants doubt. It introduces instability into established models. And in science, that's how revolutions begin, quietly, with a single anomaly, a signal from deep time that doesn't behave the way it should. In the next part, we'll explore the most dramatic explanation yet, that ID 830 may have just devoured something enormous, a primordial giant star, and that for 300 years, it may have burned with a fury we can barely imagine. Because if that's true, then what we detected wasn't just a growing black hole. It was the afterglow of a cosmic execution. And that story is even more extraordinary. Let's imagine the scene. 12 billion years ago, the universe was young, chaotic, dense, still figuring itself out. Galaxies were smaller, gas clouds were thicker, stars were stranger. And somewhere in that early cosmic wilderness, a black hole was waiting. ID 830 wasn't always 440 million solar masses. At some point it was smaller, hungry, surrounded by primordial gas, hydrogen and helium forged in the Big Bang. But something happened, something violent. Because to grow 13 times faster than the Eddington limit, you don't just sip gas, you devour something enormous. Yet the researchers behind this discovery suggest a dramatic possibility. ID 830 may have torn apart and swallowed a massive primordial star. Not a star like our sun, not even a star like the largest ones we see today. We're talking about a hypothetical early universe giant, possibly hundreds of times the mass of the sun. These are often called population 3 stars. They're theoretical. We've never directly observed one. But models suggest they were different from modern stars. The early universe had almost no heavy elements. No carbon, no oxygen, no iron. Without those elements, gas cooled differently. Stars could grow much larger before stabilizing. Some simulations suggest they could reach 300, even 500 solar masses. Imagine that. A star so massive it would dwarf anything in our modern galaxy. Now imagine that star wandering too close to a growing black hole. That gravity doesn't negotiate. As the star approaches, tidal forces stretch it, at first subtly, then violently. Its outer layers begin to distort, then tear. Spaghettification, that's the technical term. The star would be pulled into a long stream of plasma, ripped apart by gravitational gradients. Matter would spiral inward. The accretion disk would thicken. Temperature would skyrocket. Radiation would intensify. Jets would flare. And for a brief cosmic moment, ID 830 would ignite like a beacon. This could explain the super-Eddington accretion. When such a massive object is disrupted, the rate of infalling matter can temporarily exceed theoretical limits. Gas density becomes extreme. Radiation gets trapped. Instead of pushing material away, photons are dragged inward with the flow. The black hole effectively chokes on light. And during that period, growth accelerates dramatically. Yet the researchers estimate that this extreme phase may have lasted around 300 years. 3 centuries. That's all. 300 years in a universe nearly 14 billion years old. But during those 300 years, ID 830 may have gained mass at a staggering rate. Think about the scale. If you compress hundreds of solar masses into a feeding event, and if the black hole was already massive, the luminosity would be extraordinary. X-rays blazing from the inner disk, and radio jets punching through surrounding gas, energy output rivaling entire galaxies. And that energy didn't just vanish, it expanded outward, photons racing at the speed of light, crossing intergalactic space, while galaxies merged and evolved, while new stars ignited, while our Milky Way slowly assembled. That burst of radiation traveled, uninterrupted, for 12 billion years until one day it entered Earth's atmosphere. And not as a dramatic flash in the sky, not as a visible explosion, but as faint signals captured by radio telescopes and X-ray observatories, data, numbers, spectra, and within those spectra, a story. Now here's what makes this even more profound. If ID 830 did consume a primordial giant star, then we are indirectly witnessing the death of one of the first generations of stars in the universe. A star that lived and died before our galaxy fully formed. A star that may have existed less than 1 billion years after the Big Bang. We didn't see the star itself, but we saw the aftermath of its destruction, encoded in radiation, frozen in time. That's extraordinary, because astronomy is often about light that simply shines. But this is different. This may be forensic astrophysics, reconstructing a cosmic crime scene. The suspect, a supermassive black hole. The victim, a primordial giant star. At the evidence, super-Eddington luminosity and dual-mode radiation. And the timing matters. 300 years. Why is that important? Because if the super-Eddington phase was temporary, that helps preserve some of our existing models. It suggests that black holes don't permanently ignore the Eddington limit. They bend it, briefly, under extreme conditions, like a pressure valve releasing. After the feeding frenzy ends, the system stabilizes. Accretion slows. Their radiation balances. Growth returns to more normal rates. That's a comforting thought for theorists. But even temporary violations change the math. Because if early black holes experienced multiple such bursts, they could reach supermassive sizes much faster than predicted. And that has consequences for everything. Galaxy formation, chemical evolution, cosmic reionization, even the large-scale structure of the universe. It suggests that the early universe may have been punctuated by short, explosive growth events, black holes rapidly inflating, then calming, then inflating again, like cosmic heartbeats. There's another unsettling possibility. What if this wasn't a rare event? What if primordial black holes frequently consumed massive stars in dense early galaxies? What if ID 830 isn't unique? Yet we might just be seeing the brightest example because it survived long enough and shone brightly enough for us to detect. Remember, we only see objects that emit enough radiation to reach us. For every ID 830 we detect, there could be dozens we never see. Silent giants. Now think about the psychological scale of this. 300 years of extreme luminosity. If an advanced civilization had existed nearby at that time, their sky would have been dominated by a blazing quasar. Night never fully dark. Jets carving through space. High-energy radiation bathing nearby regions. It would have been apocalyptic. But for us, it's just a faint X-ray signature in a detector. Because time protects us. Distance protects us. We are witnessing violence safely from 12 billion light-years away. And yet, there's something deeply humbling about that. The universe doesn't move gently from simplicity to order. It thrashes, it experiments, it creates monsters early, and those monsters shape everything that follows. In the next part, we zoom out. Because ID 830 isn't just about one black hole, it's about what it means if the early universe allowed this kind of rapid growth, if our cosmic timeline is wrong, as if black holes were building galaxies faster than we thought, if the cosmic speed limit is more flexible than physics textbooks imply. And if that's true, then we may be standing at the edge of a quiet revolution in astrophysics, because sometimes it only takes one ancient signal to change the entire story of the universe. Let's step back. Forget the equations for a moment, forget the telescopes, forget even the name ID 830. What does this actually mean? We just detected radiation that began its journey 12 billion years ago. That alone is staggering. But what truly matters is this. That ancient signal is telling us that something in the early universe grew faster, brighter, and more violently than our models predicted. And when models don't match reality, reality wins. For decades, astrophysicists have built simulations of the early universe. You start with the Big Bang. Matter spreads out. Tiny fluctuations in density grow under gravity. Dark matter halos form. Gas collapses. The first stars ignite. Black holes form from stellar collapse. They grow steadily, limited by the Eddington rate. Galaxies assemble around them. Order from chaos. It's elegant, mathematically satisfying, but ID 830 throws a wrench into that elegance. Yet because if a 440 million solar mass black hole already existed when the universe was only 15% of its current age, then something happened faster than expected, maybe much faster. And when that happens, scientists are forced to ask uncomfortable questions. Were the first black hole seeds much larger than we think? Instead of forming from normal stellar collapse, could some have formed from direct collapse of massive gas clouds? There's a theory called the direct collapse black hole scenario. In this model, instead of forming a star first, a dense primordial gas cloud collapses straight into a massive black hole, maybe 100,000 solar masses right from birth. If that's true, then ID 830 didn't start small. It started big. And that changes early growth math dramatically. Or maybe super-Eddington accretion wasn't rare. Maybe in the dense, chaotic early universe, black holes frequently exceeded the so-called speed limit. Maybe the Eddington limit is more of a guideline under extreme primordial conditions. If so, then our understanding of black hole feedback, how they regulate galaxy growth, needs revision. Because black holes don't just sit quietly at galaxy centers, they shape their environment. Jets heat interstellar gas. Radiation ionizes hydrogen. Outflows suppress or trigger star formation. And if early black holes were growing explosively, they could have influenced galaxy evolution far earlier and more aggressively than we thought. Now zoom out even further. We are talking about events that occurred less than 2 billion years after the Big Bang. That period is crucial. It includes the era of reionization, when ultraviolet radiation from the first stars and quasars reionize the neutral hydrogen filling the universe. We still don't fully understand what drove reionization. Was it mostly stars? Or did early quasars contribute more than expected? If objects like ID 830 were more common, then early quasars may have played a larger role in reshaping the cosmos. That would shift our cosmic narrative. And here's something even deeper. Black holes are often portrayed as cosmic endpoints, things that swallow light, final destinations. But in reality, they are engines. They convert gravitational energy into radiation with astonishing efficiency. A feeding black hole can outshine entire galaxies. In the early universe, they may have been among the brightest objects in existence. So instead of thinking of black holes as just destroyers, we might need to think of them as architects. Architects of galaxies. Architects of cosmic structure. And ID 830 may be one of the earliest examples of that role. Now here's the part that gives people chills. The light we detected from ID 830 began its journey before Earth existed. It traveled for 12 billion years, while continents formed, while life evolved, while dinosaurs rose and fell, while humans learned to build tools, while civilizations emerged. That radiation was already on its way, moving silently through expanding space. And only now, in 2026, did we build instruments sensitive enough to catch it. That means the universe has been sending us messages for billions of years. We just weren't listening, or we couldn't hear them yet. And that's what makes astronomy so powerful. It's not just observation, it's time travel. Every deep space detection is a message from the past, and sometimes those messages whisper, sometimes they shout. ID 830 is shouting. It's shouting that the early universe may have been more extreme than we imagined. It's shouting that growth can happen in bursts, that limits can bend, that chaos can produce giants quickly. And here's the exciting part. This is probably just the beginning. New observatories, more sensitive X-ray telescopes, next-generation radio arrays are coming online. Surveys are going deeper, looking farther back in time. If ID 830 exists, there may be others, even older, even more massive. We might find black holes that formed only a few 100 million years after the Big Bang, and if we do, then the story of how the universe built its first structures will need rewriting. Science doesn't fear that. It thrives on it. Every anomaly is an opportunity. Every contradiction is a doorway. ID 830 is not a crisis for astrophysics. It's a clue, a reminder that the universe is under no obligation to be simple. Now think about the poetic symmetry of this. At a black hole, something that traps light, has just illuminated a flaw in our understanding. The darkest objects in the cosmos are helping us see more clearly, and that's the beauty of discovery. We don't just learn about distant objects, we learn about our assumptions. We learn where our confidence was premature. We learn where nature is more creative than our equations. 12 billion years ago, a black hole fed with impossible hunger. For maybe 300 years, and it blazed brighter than it should have. Then it calmed. Galaxies continued forming, stars were born, planets assembled, life emerged on at least one world. And billions of years later, intelligent beings pointed instruments at the sky and saw the echo of that ancient feast. That's what this discovery really is. Not just a black hole, not just a quasar, but a reminder that the universe is still surprising us, still challenging us. It's still revealing chapters we didn't know existed. And if one ancient signal can shake our models, imagine what the next one might do. Because out there, beyond what we've mapped, the early universe is still sending light, still carrying secrets, and somewhere, right now, another 12 billion-year-old signal may be on its way. We just haven't detected it yet.